Welcome to the Application Binary Interface, ABI, mini lecture. This mini lecture contains examples of how the Application Binary Interface provides a set of rules that allows independent pieces of software to work together to form a single application. An Application Binary Interface, ABI for short, is a hardware-level interface between two pieces of software. It answers the question, how does my code work with existing code, without requiring agreement beforehand about that interface. For example, consider libraries. These are independently developed pieces of code that you would like to leverage, but you don't agree on how to actually use the hardware to pass information back and forth. You can think of the ABI as a common language that all software that abides by that ABI speaks. This includes how to pass arguments to a function, how to pass a function's return value back to the caller, which registers can the callee clobber, i.e. caller saved registers, which registers must the callee save and restore before returning back to the caller, i.e. callee saved registers. How is data laid out and represented in memory? How do we make system calls? And lastly, how do we use the registers that the hardware provides us? So previous to this course, you probably heard of an API, an Application Programming Interface, and are wondering, it sounds similar to an ABI, how are they different? Well, an API is a source code level interface between two units of code. For example, public methods in a class, or functions provided by a library. API specifies what functionality exists, while the ABI specifies how that functionality interworks using the shared hardware resources provided by the processor. This isn't necessarily a low-level interface. So API, high-level and hardware independent. ABI, low-level, hardware dependent. Programmers focus on APIs. In fact, most of your time in this course, you'll be focusing on the APIs provided by libraries and the Linux kernel itself. Tool writers, on the other hand, for example, compiler backend developers, focus on ABIs because they need to produce code that works together without agreeing on the interface beforehand. So why should you know the ABI, especially if you're going to spend most of your time in this course focusing on APIs? Well, if you write enough assembly code, you'll eventually need to know the ABI being used by your compiler. So you'll see a lot of overlap between why you use assembly code and why you need to know the ABI. For function level optimization, if you're ever going to write firmware, if you want to write code that works at the hardware software interface, and if you're going to be a cybersecurity professional. That being said, who cares about the ABI? Well, security practitioners, reverse engineers, game developers, embedded system programmers, operating system and virtual machine writers, and compiler backend writers. Basically, anybody who writes enough assembly eventually has to care about the ABI. Now that I convinced you to learn more about the ABI, you'll want to know where to go to find information about the ABI that governs the system that you're going to use. Well, you should know ABIs are processor dependent. Even comparing x86 32-bit and x86 64-bit, they're governed by different ABIs. ABIs are also operating system dependent. You might not be surprised to learn that Windows and Linux have different ABIs. You might be surprised to know that ABIs could even be tool dependent. So for example, GCC on Windows and Clang on Windows, so two C compilers on the same operating system, implement two slightly different ABIs. So since this course is focused on x86, where can you find information about x86 ABIs? Tried and true Wikipedia is one good source. You can also go to Intel and Microsoft for information on the ABIs that they implement. To start the ABI demonstration, let's take the program from our inline assembly mini lecture. So what we're going to do for the ABI demonstration is we're going to take this inline assembly and we're going to basically promote it to assembly file in and of itself. Now, why would you want to do this if, as we showed you from the inline assembly lecture, we can get a lot done just by including assembly in line with our C statements? Well, one example is some tools don't support inline assembly. So you have to use external assembly files. One example of such a tool is the TI MSP430 compiler. Another reason is, as your assembly statements grow in complexity, good coding practice dictates that you remove them from inside of the C statement and make them a function in and of themselves. And when you do this, you must know what the ABI is. The first modification that we have to make is to remove the inline assembly statement. Once it's removed, we're going to replace it with a call to our assembly function. Because I'm creative and I know we're going to make the assembly function, I'm going to call this function do nothing. And it behaves just like any other function. So now I'm going to call an assembly function, or a function implemented in assembly, named does nothing. Now this function will not be defined inside of the C file, so I have to tell it that this function is actually implemented external to this file. And so I'll say returns nothing because it doesn't do anything, for at least right now, and it takes no arguments. There we go. So now I've said, hey, I want you to be aware that there's this function that exists that matches this prototype. It returns nothing, doesn't take anything, and it's called does nothing, and I call that function in my C file. So I'll save that, and now I have to implement my assembly file. So I'll call this ABI.s. Okay, and so because we're in assembly, I have to give some low-level information. I say I want you to put the following in the text section, which is where the code goes. I'm going to define a global, meaning it gets exported outside of this file, calls does nothing, and I'm going to define does nothing as a label, so the entry point of the function, and give it its name. And because I'm not going to look at the ABI, I want to see what happens when I just try to implement some assembly, even the simplest assembly, without looking at the ABI. I'm going to put a few no ops here. So remember from the inline assembly lecture, these instructions don't change the state of the processor beyond incrementing the PC and taking a small bit of time. So I'm going to save this, and now let's try to build it. So we're going to use Clang like we did before. We're going to turn on all of the error reporting. I'm going to turn off optimization for right now. And we're going to output this as asmfunc.bin, and we are going to tell it that it needs to know abi.s and asmfunc.c. Okay, that seems to have worked. Before we run it, let's check object dump and see what it looks like at the assembly level. Okay, as before, we'll search for main, and we see the main function described here. This is the assembly the compiler came up with here, and we can see we're going to call to does nothing. And because we actually passed it the compiler ABI.s before we did the asmfunc.c, it populates the text section with the results of does nothing before main, and you can see does nothing is simply no op, and then some padding. Okay, so everything might look good, but we'll see what happens. So we'll close that, and so let's try to run, see what happens. Well, it turns out it's misbehaving a little bit. So what can we do to fix it? If I have a function, I actually need to return from this function. So I'll put a return statement at the bottom of our does nothing assembly function. I'll save it, and I will rebuild. Then I'll execute it, and we get the expected result. Hello world 42, goodbye world 24. And just for fun, we can check the object dump and see here that again we have no op, no op, no op, and then we have our return instruction, and then some padding here, and then in main, nothing changed. So we got the call from does nothing, but now we correctly go to does nothing and then returns control flow back to main as we would expect it to. Okay, so that's a very simple assembly function. Probably want to do something a little bit more complex. For example, let's return a value now. So we're going to go back into our code, and I consult the ABI for x86-64, and it says to return a value, you put that value inside of the register RAX. Okay, so I will clear these values out here. And I'll move the value 1 into RAX. I'll save this, and I'll switch to my C function. And in my C function, so now I have to save the value that does nothing returns. So I will create a new variable, Z, that's unsigned int, that it gets the value. I also need to change the prototype from does nothing so that it now returns an unsigned int. So now we call does nothing, it returns a value in RAX. That value gets stored in unsigned int Z, and we will update our print statement so we can see the value of Z. And so now we will build and run, and instead of goodbye world 24, which we saw before, we now see the return value of does nothing, which is 1. And so now if we want to object dump to see what the assembly that was produced by Clang, we run object dump and search for main. And so we're in main here. We can see that this move after the call, the instruction that executes directly after the return and does nothing, is here, which is moving the value of EAX into the stack. So as you're updating a variable, and if we click and does nothing, we have our move the value 1, the immediate value 1 into the register RAX, and then a return instruction. Okay, so now that we know how to return a value from an assembly function, let's learn how to pass it parameters. So I'll start out in my C function, and I'll update the prototype. And I'm going to make does nothing take 2 parameters, both unsigned ints. And then when I call does nothing in the body of main, I'm going to pass it X and Y. And so does nothing will take X, Y, and return a value that we store in Z. And hello world will print out X, and goodbye world will print out Z. Okay, so that is our C function. So inside of our assembly function, let's start out by doing something pretty simple so we can just see that we are actually getting the parameters that we think we're getting. So I'll do a simple modification of the parameters that I'll shift them left, and I'll shift them left by 1 bit, which is effectively multiplying by 2. And I look at the ABI, and the ABI says, oh, one of the parameters is in RDI. Okay. Then I want to have this effect carry over to the return value so I can actually see it when I print it out using printf. And so instead of moving 1 into REX, I'm going to move the value in RDI into REX. Okay, I save it. We build it, and we run it. And again, we see hello world 42, and then we see goodbye world 84. So that confirms that, in fact, RDI contained the first parameter's value, which was X. And so since we shifted left, one time, that's effectively multiplying by 2, we would expect goodbye world to print 84. And that is what we see. Okay, so now let's see what happens when we access and modify the second parameter. Looking at the ABI, tells us the second parameter, y in this case, is passed in RSI. So we'll change this to shift RSI left by 1, and then move that result into RAX. We save. We compile. And then let's see. So we know that y was 24. 24 times 2 is 48. And in fact, we see that does nothing printed 48 or returned 48 in this case. So now we can see how we can take two parameters that are passed in registers, modify them in our assembly function, and then return a value. So in the last example, we saw how to pass unsigned integers to our assembly function. But what about pointers? So to understand how to pass pointers to our assembly function, we'll change one of the arguments to a pointer. Let's do the last one. And instead of sending the value of y, we're going to send the address that holds the value of y. Okay, so we have updated our program there. And let's see what changes we need to make to our assembly function. So we'll focus on y since that's the only parameter that we changed. And so we're going to get the value of y. We're going to shift it left by 1, multiply it by 2, and move that value into the return register REX, and then we will return. So let's do that and see what happens. So we compile it, and we run it, and we get a very large negative number. So what went on here? Well, again, we're passing a pointer, not just directly passing a value. So even in assembly, we need to dereference that pointer. So I look at the x86 assembly reference, and I see that I can dereference a pointer by putting parentheses around it. So I will take the value RSI. So that is that value that I'm taking is actually the address that holds the value of y. And so by putting parentheses around it, it says take whatever is at that address as the value. And I'm using the move instruction, so I'm saying move that. And I'm just going to move it into RDI for right now. And then I can shift RDI left 1 and then move that value into REX and then return. So let's save it, rebuild, and rerun, and we see goodbye world 48. So again, remember y started out as 24. We gave it the address of the memory location that stored that value of 24. In the assembly file, we dereferenced that address to get the value 24 again. We doubled it by shifting it left 1, stored it in the return register, returned, and printf printed out that current value, which is 48. So it turns out that as long as you're dereferencing correctly, both traditional values and pointers can be passed in registers. When calling functions, there are two types of registers to be concerned about: callee saved and caller saved. Caller saved registers are the registers that the calling function backs up and restores across the function call if it needs to depend upon those values. In contrast, the callee saved registers are registers that the calling function assumes will be kept intact across the function call. So it doesn't waste time actually backing them up when it calls a function. Now, if the callee decides that it need to use those values and overwrite them, then it's its responsibility to back up and restore those values before returning to the caller. So far, when we've modified RSI, RDI, and RAX, we've only been dealing with caller saved registers. Let's see what happens when we start having to deal with callee saved registers. To see what happens when we modify callee saved registers, we first need to understand which registers are callee saved. To do so, we look up the ABI for the processor that we're using, in this case x86-64, and it tells us that one of the callee saved registers is RBX. So instead of using RDI, we are going to change the destination register to RBX. So now when we dereference RSI, remember that Y is RSI and Y is a pointer, so we dereference it, get in its value, and we move that value into RBX. Now RBX is a callee saved register, which means that main, which calls does nothing, assumes that if does nothing is going to overwrite RBX, it first backs it up and then restores it before returning back to main, which we are not currently doing. So this is called clobbering. So does nothing is going to clobber the current value of RBX by overwriting it. Then we're going to shift RBX 1, and then we're going to take that result and we're going to return it back to main, and then we're going to return. So in this case, we've taken the register RBX, which is supposed to be callee saved, clobbered the value that main expects to hold, the value that it did when it called does nothing. So we'll go back to the C source code. So to increase the chances that main actually relies on the value of RBX, we're going to shift things around a little bit. So first thing I'm going to do is take this print statement of hello world. I'm going to move it up here, and then I'm going to need to save some state. So I'll just put a loop around this does nothing and goodbye world print statement. And again, this is just to increase the odds that main needs the value of RBX to be retained. So we'll save, and we will compile, and then we'll run it. And in this case, it prints out the first time 48 correctly, and then we get a segmentation fault. So let's actually look at the disassembly to see what's going on and why this might be occurring. So we'll use the object dump tool on the binary, and we'll dump that to a file. And then let's go to main. Okay, so we're in main here. Let's look at our call to does nothing. Okay, remember does nothing clobbers RBX. And you can see right before, RBX has a useful value which would be loaded into RSI, which tells us that RBX is synonymous with Y. And so we go down, RBX is never being overwritten. And then we go to this compare and this jump. This implements our for loop, and we jump back up to the start here. And again, what happens is you are loading the parameter in, calling does nothing. And so what happens when we overwrite RBX, we are in turn corrupting the parameter passed to does nothing, which eventually causes a segmentation fault, likely when we try to dereference the pointer. So that explains what is happening and why we get a segmentation fault. Let's see how to actually save and restore callee save registers correctly. So let's go back into our source code. The C source code doesn't change. The problem is in our assembly routine. So go to our assembly source code. So it's pretty simple, saving and restoring callee save registers. So first you identify any callee save registers that you clobber in your assembly function. Then for every callee save register that you need to save and restore, you first save it by pushing it to the stack. So we use push and then RBX. Now once we push it to the stack, it's saved in memory. We're free to do whatever we want to it. And then before we return, we simply need to pop it from the stack. The only caveat is you need to kind of make sure the order is correct between your pushes and your pops. So if we pushed 3 different registers to the stack, we would need to pop them from the stack in the reverse order. Okay? And so now we will save this, and we'll go back, and we will rebuild the program, and we will run it, and we'll say now it prints out 10 times correctly because we are correctly saving and restoring the callee saved register that we clobber, RBX. Okay, so now that you know how to call an assembly function from C, what about calling a C function from assembly? So let's go to our source code. We'll start off in our C source code. So we will create a new function in the C source code. And again, because I'm creative, we'll call it does something. It takes 2 arguments, and it's going to return. We're going to shift except for by 1, then we'll add y shifted by 1. So basically 2x plus 2y, and it'll return that. Okay. So now we added another function. Let's go to our assembly function. Okay, so let's work in our assembly function here. Let's call does something here. Okay. And we need to tell it that there is an external name, does something. Okay. And so now we have this. Okay. Let's build it and see what happens. Okay. Doesn't seem to change the behavior of our program. Remember, does something has 2 arguments, x and y, both unsigned integers. So we need to match those up correctly. Just as we did from going from C to assembly, we need to prepare the registers going from assembly to C. But before we do that, we need to back up our caller saved registers. So in this case, we know we're going to contaminate the registers used to pass the parameters. So once RDI, so we're going to push RDI. We're going to push our SI, right? Okay. Now that saves our version of the registers. Now we can modify them to make them appropriate for does something. So we're going to move whatever's at the address contained in RSI. Then we're going to take that value, and we're actually going to say put that value in RSI itself. So remember, does nothing takes a pointer, where does something takes an actual unsigned integer. So we're going to dereference that value, the pointer value, and move it into RSI. RDI doesn't change because we're going to use the same argument that we did before. So, but we still need to back it up because we don't know what does something will do. So we have to be safe. It's a caller saved register, so we have to save it. Okay, so now we are free to call does something, and then after the call, we can restore. So again, remember we have to restore pop in reverse order that we push. So RSI, and then pop RDI. Okay. And then now we can use the value that's returned. So let's say we're going to take RAX and we're going to add whatever that value was from does something, and we're going to put it in RBX, which was our current working value here in does nothing. So we do that. Then we move RBX into RX because we're going to get ready to return it to main. And then we restore the callee saved register, RBX that we clobbered, and then we return. Okay. So we get all that saved. We rebuild. And we run. And we now see the program gives us the expected behavior, which is 48. And then we added it to 2x plus 2y, which equals 84 plus 48, which is 132. 48 plus 132 is in fact 180, so we get the expected correct behavior. I did want to highlight one point before going on to the next topic. So notice in here, I am saving and restoring more registers than I need to. So for example, if I look at the tail of my assembly function, I am using the value rbx. I use rax, which comes from does something, but I actually don't need to save and restore rsi and rdi. So I can optimize this. My goal is to kind of teach you the requirements that you have to have in general, but the beauty of assembly, or sometimes the burden of assembly, is you can optimize many of the unneeded operations away. So if I just make this minor optimization, I am sure there are more that I could do, and save it and rebuild and rerun, you'll see I get the same values. I just wanted to make that point for those of you out there who are pedantic, that yes, I'm not hyper optimizing it. It turns out that calling a function from assembly is a little bit more complicated than I presented in the last example. To kind of highlight this complication, let's take a look at a slightly modified example to kind of tease out where things fall apart. So if I go to our does something function, and inside of it I'm going to use a little bit of inline assembly, which you can see from the previous lecture. I'm going to push a value. I'm going to be explicit. I want to push RDI. Then I'm going to move DQA from offset 0 from the stack pointer, and take that value and put it in special register XMM1, and then I'm going to pop RDI, and because I'm specifying everything explicitly, there are no inputs, no outputs, and there are no clobbers in this. Okay. It's not really important what this actually does. It's just meant to have some behavior that will tease out not following strictly what the ABI says about calling functions. So we'll save this, and I'll build it to check for errors, and that looks good. As a double check, let's look at the object dump. Go to main, and then so we got does something, and so you see here that we have our inline ASM is put in here, where we have that move, we have the push RDI, then we move DQA instruction from 0 offset off the stack and put it in the XMM1 register, which is a register for an instruction set extension, and then we restore RDI. Basically, my goal here was to use this move DQA instruction, which targets the XMM1 instruction. But because I want to have good behavior, I saved and restored RDI register around it. Okay, but the reason why I'm using this instruction is the instruction takes advantage of a kind of a specific rule in the ABI for x86-64. That rule is that when you call a function, it must be aligned at a 16-byte level. And so this instruction assumes that alignment, and the compiler assumes that alignment too. So when the compiler assumes that alignment, it will adjust the current stack alignment when it uses this instruction. If that alignment is not correct because you've given it a hand-coded assembly routine, then bad things will happen. So let's see what happens. when we run our function, everything looks good so far. So let's go into our assembly. Okay. So we know when we're called with a 16-byte alignment, but a return address is put on top of the stack. So we're on x86 64, so a return address is 8 bytes, 64 bits. So now when we're at this point, we're at the push, we have 8 bytes alignment. But again, when we get down to does something, calling does something, we need to be at 16 bytes. So we push a 64-bit register. That puts us at 16-bit alignment. So that is in fact why this is working. Okay. So in this case, let's get rid of clobbering RBX so we don't have to store it anymore. So we'll do this. We'll move that. We'll do this a little later. Okay. We can clear this. So now we're dereferencing y, taking the value that y points to, putting it in RSI, which fits directly with what does something expects. RDI is unchanged. It's common between does nothing and does something. And then when we return from does something, we will take our shift. We will shift 1. In this case, it'll be RSI. So again, that's y times 2 at this point. Okay. Then the next thing we will add, in this case, REX and RSI. And then we will just return. But I need to make sure I get this order right here because we'll save this. So this is a very small, fairly optimized assembly routine. And again, when we call does nothing, X is passed as RDI. The pointer Y is passed in RSI. We dereference that pointer to get the value, and we put that value back in RSI. Does something expects 2 unsigned ints, X and Y. So X is passed in RDI, which is the same as it was for does nothing, so that remains unchanged. Y is the value of Y, which is passed in RSI, so that's fine. We take that value, does something returns a value in REX. We take RSI, the value of Y, we shift it by 1, and then we take that result, add it to the result of does something, and then return that result back to main. Okay. So, but note, the thing we care about is the alignment when we call does something, and you can see, remember when we call does nothing, after the return address is placed on the stack is 8-byte aligned, not 16-byte aligned. So when we call does something, which has that special instruction we added that assumes alignment, it is now misaligned. So we saved it, we're going to rebuild, and then we run. You see we get a segmentation fault because we did not respect the alignment guarantees. Now, most of the times you could get away with this because most instructions don't have alignment restrictions, but when you're using some of these instruction set extensions that do, the compiler will always assume you're abiding by the API. Otherwise, it'd have no clue about what alignment the stack is at. In our last example, let's see how to call a variadic function like printf. Okay, so let's go into our source code. Okay, so the first thing we want to do is want to have a nice little message to print. So we put that in the data section. Okay, and so we'll just call it format string, and we're going to use a special directive called ASCII Z that says this is an ASCII string, and terminate it with the null terminator. So we'll do a kind of fancier hello world, but something very similar to what you would see in C. Okay. So we have this, and what this does is it says in the data section, allot some space, label that space FMT_str, and in that space put the contents of the string followed by the null terminator. And so now we have the space in some other part of memory that has this label format string. Okay, then we have our section's text. In this case, we are not going to make use of does something. We're going to call this assembly function from C. So we have to say global does nothing. So the global symbol does nothing. And also we are going to call the function printf. So we need to say I have an external symbol printf that you should know about that I can use in this assembly function. Okay. And then in does nothing here, we can go back to, let's just clear this up right now actually. Okay. So first thing we'll do is we'll back up any callee saved registers, so RBX, and then I need to move, and I'm going to take that label format string, and basically what I'm saying is give me the value of that address, and then I'm going to move that into RDI. So remember, printf, it takes the address of a format string. So remember we reserved space in our data section, and we gave a label to the address that starts our format string, FMT_str. So we take that and we load that into the basically the register that's used to represent the first parameter to a function. So printf is just like any other functions, except for it takes a variable number of parameters, which we'll see why that's important in a second. So we do that. Okay, then we are going to move. We're going to take the value 42 and we will put that into RSI. And while I'm doing that, I'm trying to mimic this hello world. I want to print 42 because it's the answer to life, meaning, and everything. And so just like you would in C, you can use the format specifiers that you would in printf. It's the same. So remember, this mimics the printf So basically this mimics this statement here. And so you can see the first argument RDI is the string. The second one is the value that we want to do. And so in this case, the value is 42. Okay. So we set up the parameters correctly. And then now, since that's done, if it was a normal function, we could just call printf. And then once we're done with printf, we can restore any callee saved registers, and then we can return. Okay. And you might think, okay, well, I know Professor Hicks mentioned that he wasn't going to optimize this, but you clearly aren't using RBX, so why are you pushing it and popping it? Well, remember from the previous example that when I call printf, I have to have 16-byte alignment, and that when I go into a function, the return address has been placed on top of the stack, and since we're on x86-64, that's 8 bytes, so we're at 8-byte alignment, so I just have to push something on the stack that's 8 bytes, so I'll just choose RBX, and then I'll pop it so that by the time I call printf, I do meet the requirement of 16-byte alignment as specified in the ABI. Before we compile and run, there's one last change we have to make to complete our call to printf. The printf function is what we call a variadic function, meaning it takes a variable number of arguments. So the ABI specifies that for such functions, we need to specify the number of floating point arguments the function takes that are passed in the floating point vector registers. So in this case, we are not using any floating points, and none of them are definitely passed in the vector registers. So we're going to pass the value 0, and we're going to update the value RAX. In production code, you'd often see, instead of updating the entire value of RAX, you'll see just the least significant 16 bits are updated with the value 0. And this signifies that, well, the maximum value is 8, so anywhere from 0 to 8, all of those values fit in the least significant 16 bits, so we can save a little space and just update the least significant bits of RAX, and the hardware will take care of extending that out to the entire register. And so now we are ready to save and compile this and run it. And we see that, as expected, we get a hello assembly world 42, because remember that we passed as a parameter to printf the value 42, and it's printed out 10 times. Just like we did for the inline assembly mini lecture, let's look at where we see the ABI in use in the real world. So we'll go back to the same project, the GNU Multiple Precision Arithmetic Library. And in this case, we're going to be in gmp/mpn/x86_64/gcd_11.asm. So in this case, we have a full assembly file written out, and you can see here how they take care of alignment issues, have function prologues. So clearly they're making ample use of the C preprocessor, and you can see here, in this case, this is ample enough complexity to warrant a full-fledged assembly file, and the assembly file works in with a larger C-based application. So let's recap what you learned about the x86-64 ABI in this mini lecture. So assembly code must respect the platform's ABI to work with other code that you didn't write. The calling convention dictates passing arguments in registers and on the stack. Arguments are placed into registers from left to right, but pushed on the stack from right to left. You return scalars and pointers in RAX. The stack pointer needs to be aligned by 16-byte multiples before calling another function. You learn the difference between callee saved registers and caller saved registers, and a function's clobbers determines the registers that must be saved and restored by that function. And lastly, you saw that variadic functions have special requirements on the value in the register AL. Beyond the links provided earlier for the platform-specific ABIs, I found this reference. It is from a book chapter that documents the x86 64-bit ABI.